Hi. So this is so Berend von Starkenburg is visiting here in Bloomington, and actually visited in February, I believe, and also will be visiting again in the fall.
Okay.
So he has a kind of long-term relationship to be here, and he's actually a grad student in Leiden, in the Netherlands, and he's going to tell us about his work on Sheaves theory and separation logic. So, like I was saying before, so everybody should feel free to ask friendly questions during your friendly talk.
Thank you for the introduction, and it's good to see so many people. So, as Larry said, this talk will be mostly about separation logic. This talk is based on the talk I gave earlier from computer science, theoretical computer science seminar. So it will be related strongly to computer science. That's also why the term process composition is in the title. It's related to separation logic, and it also arises as a byproduct from my Sheaves theoretic model, and you'll see how it looks like. But let's try to keep it like understandable for people with not that much background in theoretical computer science. So yeah, I will provide category theoretical model for the semantics of separation logic. And the goal of that is to see what is at the core of separation logic. So what I will do is first we'll give the background of separation logic to establish a common ground. Because my category theoretical model is based on sheaves, an explanation and some examples of what sheaves are is also necessary. And afterwards I will explain how I kind of build or construct the category theoretical framework step by step, and examples to make the design choices more understandable. Okay, so if you're dealing with complex systems and we want to reason about them, we would like to divide the system into smaller, more understandable components and reason about those components individually. The problem with this is that when we do this, we afterwards need to see how these components fit together in a meaningful way. Separation logic is a logic that is designed to facilitate this. So it allows for reasoning about local components of a complex system and see how those components then fit together to provide a global specification of the system. For the pointer model of separation logic, we are dealing with memory that the system uses. The state of this memory is described by assertions, and assertions are in this case first order logic formulas, extended with some formulas that tell something about the state of the heap or the memory. And these extended logical formulas are the empty formula, the singleton heap, the separated conjunction, the separated implication. We will later see,
Would you shift over a little bit? You're standing.
You're standing in the slide.
Yeah. So later on we will see what the separated conjunction and what the meaning of the separated conjunction and the separated implication is exactly. In the top right example, you will see an example of the singleton heap. We have some variable x. X represents an address, and the address of the memory contains two consecutive cells, one cell containing the numeral 3 and another cell containing the variable y. Aside from the assertions that describe the state of the memory, separation logic also allows for reasoning about computational effects that modify the state to memory. And this is achieved with the use of OR triples. You can see them here. So how OR triples work, you have two sets of assertions, the set P and the set Q. We say that the set P, the set of assertions, is the precondition. It describes the state of the memory before execution of the program. Then we have C. C contains a specification of the program. This can be a sequence of commands. And we say that the OR triple is valid if for the precondition P, after we execute the program specified by C, we arrive in a state of the memory that is described by a set of assertions Q. So, in this case, in the example in the middle, P can be described as a singleton heap x points to 3. The command is we assign the numeral 1 to x, and the post condition is then the singleton heap, the variable x points to a cell containing the numeral 1. I've already alluded to the extra operands that separation logic introduces. The first one is the separated conjunction. It is denoted by the star right there. And we can read this assertion as follows. We have some assertion P describing a certain part of the memory, and then the assertion Q describes the memory, but that memory is disjoint from the memory that P describes. You can see an example on the top right. So you have,
Is memory the same as heap?
the memory is the same as heap. So in the top right example, we can see the first assertion. There is some variable x that points to a cell containing 3, and then another assertion. Y points to a disjoint cell, like a cell separated from the cell that x points to, and that cell contains also 3. This is a simple example, but it can become more complicated when cells are referencing each other, which is seen in the middle example. So we have a variable x containing that is pointing to two consecutive cells, one containing 3, one containing the variable y. And for the disjoint part of the memory, we have a variable y pointing to two consecutive cells, one containing 3 and one containing x. But because the variables point to disjoint parts of the memory, it should be the case that x and y must be the same variables. Then also the separating implication. If you have some assertion P0 that describes the state of the current memory, we can always extend the memory by disjoint parts, and then the assertion P1 holds, as you can see in the bottom right example. This is a more telling example for how the assertions evaluate according to the state of memory. So you have two scenarios. The top scenario where we have two variables x and y pointing to disjoint consecutive cells, and the bottom scenario where x and y point to the same two consecutive cells. So if you look at the top assertion, we have a variable x that points to two consecutive cells, both containing 4. In the bottom scenario, this holds because we have a variable x pointing to two consecutive cells, 4 and 4. But in the top scenario, it is not a valid assertion because it does not describe the entire state of the heap. It omits the fact that there is also a variable y containing that's pointing to two consecutive cells as well. Some more interesting examples is the assertion here. So we have two variables x and y pointing to two disjoint parts of the memory, both containing two cells containing the number 1. This is a valid assertion for the top example, but not for the bottom example, because the x and y point to the same part of the memory. Okay. Yeah. As I mentioned before, separating logic facilitates reasoning about smaller components of the system, and then combine these components to get a global specification of the system. This is facilitated by the following inference rule. So if we know that the following or triple is valid, so for some precondition B, if we execute the program C, we end up in a post-condition described by Q, then we can always extend the assertions P and Q by assertions that describe a disjoint part of the memory. And the thing is that because C doesn't touch any of the assertions, or doesn't touch any of the memory that's described by assertions R, the state of this memory will be the same, and the below or triple is also valid. Or if a program executes safely in small states, we can always extend it so that it operates safely in a larger state, as long as the program doesn't touch any variables in these larger states. There are some different ways of interpreting this. So if you look at the assertions R, with this notation, it should be the case that the assertions are the same set of assertions. But should it also be possible to extend the assertions of P with R and then extend the assertions of the post-condition Q with R prime, maybe some different assertions that describe a different disjoint part of the memory? And also, if you have assertions P describing a part of the memory, maybe the program C modifies the variables that are described by the assertion P in some way that it then points to a different part of the memory. So the post condition now describes a different part of the memory than it is described by the precondition. Or should they be just like, shouldn't be, just be allowed? The advantage of making a category theoretical model is that it allows for design decisions that can support multiple interpretations. So as I've mentioned before, the categorical framework will be constructed using sheaves. Let's first see what sheaves are, and I will do this by showing you an example. So let's consider all functions that are defined from the real numbers to the real numbers. We can look at functions that are defined from the entirety of the real numbers, for instance, sin of x. But we can also look at functions that are only defined on an open interval of the real numbers, which is this integral here. So if you consider functions from the real numbers to the real numbers, we can consider different families of functions, maybe global functions or functions that are only defined on an open interval. But the key point is that if we look at a function that is defined on the entirety of the real numbers, we can always restrict that function so that it only is defined on an open interval.
So we say restrict, like psi x is a function from each x real to psi x, right?
Yeah.
But if I restrict that, I will still get a function. I guess I'm not sure if your integral sign means integral.
There's no free x.
Yeah, that's what we would say. Maybe by I mean, it feels like how's the way to put it?
That's just
Yeah.
a number. It's just a
Yeah.
number.
Is that number when? Yeah, it's that. Yeah, it's just a number.
Why do you,
I'm sorry?
that what you wrote there is just a number. The integral from minus pi to 7
Yes.
sin x dx. Don't you want something that has x free in it? Doesn't have any x.
But it doesn't really make sense to look at an integral that's for numbers outside of the interval, right? Like it is not defined for, let's say, 8.
It seems like you're saying restrict sin x to the constant.
Yeah,
that's a
that's not what you mean.
Oh,
You're-
parsing the line about restriction, I think, is our problem, right? Like,
Yeah, that line of restrictions.
You don't
Or even the line above, where it says that a certain number is defined on interval. I feel like by integral you mean lambda or something. Like your integral sign doesn't mean integral. You're talking about the function that will take any x between minus pi and 7
Okay.
and return sine x, right?
That is what I like.
Yeah, okay.
points.
I don't think that's what in math.
Or are you saying the thing with the integral doesn't meet all of the definition of sine, but only the definition of
Well,
sine for that?
I'm not sure if that's a function that he makes either.
Well, I just want to look at the function of sine x is only defined from the open interval minus 7 to minus pi to 7.
Yeah, but that's not the. I mean,
Like-
that function could be fed to the integration operation.
Yeah.
But what you're talking about is not the result of that integration operation, but what you will feed to that integral, right?
Yeah. Okay.
Okay, and that thing that you would feed to the integral is the result of restricting sine x, right?
But I still don't see how like.
Please don't. Yeah, no, I don't think that's what he means either.
Yeah.
Yeah.
And so do you know what he means?
Yeah, I
Could
think
you write it down?
Yeah.
Sure,
I'm
it's-
also interested.
it's
Yeah.
lambda x sine x. It's I would just write it as sine x, but x is a number between minus pi and
But
7.
how can you, if you have lambda x sine x, maybe it's a bit out of scope of the presentation. It's just like an example to show how Sheaves operate. But in lambda x sine x, how can you specify then the interval which that is defined?
Yeah, so similarly, when you write sine x, how do I know that that x is all reals?
Yeah.
Maybe it's all complex numbers,
Yeah.
right? So just a we can all unite in our complaint about mathematical notation.
Right, I think Larry's got that.
Right.
Yeah, right.
Yeah,
That's-
I guess we finish.
Right,
Yeah.
but then it also makes the restriction line also.
Yeah, put that there, put that there.
Yes.
Yeah, don't put integral signs.
Okay,
Yeah,
but
definitely.
the key giveaway again is that if you now look at that example and then look at the smaller interval, maybe from 1 to 4, we can either restrict sin x directly from the global specification to the smaller interval, or first restrict it to the open interval of 0 to 8, and then restrict it to 1 to 4. But the defined function will be the same function. So they are compatible in a way. So here you will quickly see the definition of what a pre-sheaf is. We will still use the example of continuous functions from the real numbers to the real numbers. So what is the data of a pre-sheaf in this case? Well, a pre-sheaf goes in this case from the topological space that is the real numbers to a certain set. Open intervals are open sets in this topology. So the first datum that the pre-sheaf is the set of continuous functions that are associated with some open interval. So if you have like an open interval u, f of u contains all continuous functions that are defined from the open interval u to the real numbers. The second thing is that we can restrict these sets. So if we now have a smaller open interval v, we can restrict the set of continuous functions defined in the open interval from u to the real numbers to the set of continuous functions defined in the open interval v to the real numbers. The thing to notice for those like still familiar with calculus, restricting a set of functions to a smaller interval is a subset of all functions that are defined from a smaller interval to the real numbers. So restricting from fu to v is not the same set as fv. Again, pre-sheaves should come with some compatibility. If we look at three open intervals, the biggest one is the open interval u, a smaller open interval v contained in u, and the smallest open interval w contained in both v and u. If we restrict the set of continuous functions from u to v, then this is the same as first restricting, from u to w. This is the same as first restricting to, as you see again, from u to v, and then from v to w. So now the question is, what makes a pre-sheaf a sheaf? We will look at it now. If you look again at the topological space that is for real numbers, you can pick any open interval, let's say minus pi to 7. And then we can pick another open interval, maybe from minus 123 to 1. If you continue doing this long enough, eventually the collection of all those open intervals will cover the entirety of the real numbers. So the collection of these open intervals is then called the cover of the real numbers. If you look again at this collection of open intervals, there is a set of continuous functions from one open interval to the real numbers for each open interval that is containing a cover. Now, the thing what makes a pre-sheaf as a sheaf is some gluing action. So, and it is described as follows. If you take one function in a set of continuous functions defined from the open interval u1 to the real numbers, if that function is defined on the entirety of the real numbers, like if you look at it globally, then we can also find it in a set of continuous functions from another open interval to the real numbers. So let's say that we can find some function f2 defined from another open interval u2 to the real numbers. Then as long as the function f and f2 behave the same on the intersection of those two open intervals, so all the real numbers that are contained in u1 overlap u2, then we can paste those functions together to get a function that's defined on the combined open interval u1 and u2 to the real numbers. Now, if we do this for all open intervals in the covers, because all open intervals cover the entirety of the real numbers, eventually we will retrieve the specification of the function f on the entirety of the real numbers to the real numbers. And this gluing property is exactly what makes a pre-sheaf a sheaf. It says the following. So if we have some cover of u, and we look at pairs of functions, so we have like open interval u alpha and an open interval u beta that is in the cover of u. If the section or the function of f alpha is defined the same as the function f beta, but only restricted to the overlap of the two open intervals, then there must exist a unique section or a unique function in those open intervals combined, such that when we restrict this unique section or function to those respective open intervals, they are the same function. Now, the idea of this talk will be to show that we can capture the local reasoning properties of separation logic using the logic of sheaves. And the way we will do this is, instead of a topological space that are the real numbers, we will define memory as a topological space. And then, instead of open intervals of real numbers, we look at open sets of the memory. And then instead of functions from the real numbers, or like from open interval to the real numbers, we will look at computational effects that operate on certain parts of the memory. And the idea now is to look at computational effects defined on, or that operate on different parts of the memory. And then if we have a sheaf, it should say that if those computational effects behave the same on the overlap of those different memory regions, then we should be able to combine them to get a computational effect that operates on the combined memory region. Okay, now the way we will do this, I will show that now. So I talked about that we wanted to define a topological space that represents the memory of the system. So let's just take a set that represents a set of memory locations. Let's look. We can define like we can take the power set of those memory locations and sorry, I just lost it a little bit, but so we have the set of all memory locations look. We take the power set of that, and then we can take elements in the power set of that are like subsets of the set of memory locations. So let's say that we have a memory that is specified as this, and we look at the discrete set log. Log contains memory locations L1 to L8. We take the power set of those, and elements in the power set are these letters here. So for instance, L1 is in the power set of memory locations, so is B, C, and D. And because if we combine all those subsets together, we get back the set of memory locations. It will now form a cover of the set of memory locations. And we can also compare subsets to each other. So L1 is the smallest memory, like local memory. These will basically form the restrictions. So we can always restrict, if we like have a memory specification of L1 and L2, we can always restrict it to L1. So these inclusions, together with the objects that are like subsets of the set of memory locations, induces a pre-order category. That is this. It's here. Elements of this are subsets of memory locations, and we have maps between them. Those are the inclusion morphisms. Now we also need a way to access what contents are stored in the memory, and we'll define a function that takes as input a subset of the set of memory locations and returns the set of all maps from that smaller local subset to this set of integers. How does it work? So let's say that we look at the subset B containing memory locations L1 and L2. So it has two maps in it. As you can see here, maybe it's a little bit too small, but at the memory location L1, the numeral 1 is stored. At the memory location L2, the numeral 2 is stored. So the set of all maps from memory locations L1 and L2 contains two maps, one at the value is to 1 and one at the value is to 2. So now we have some topological definition of memory and also a way to retrieve the contents of what is stored in memory.
If you don't mind, I've got to look. So, so M takes, I'm not sure what M1 M1 and M2 are?
Oh, yeah. I think I'm just like skipping way too far ahead.
Sorry. So the lowercase m1 and m2, right?
Yeah.
They're each a map from the same indices, namely b, right? To integers.
Yeah.
But is question mark an integer? I guess maybe this one.
So there are partial maps. So for that I forgot to tell. So it we only have like two cells basically. So one cell that's and we have a variable that represents the address of these cells. And we basically want those maps that can tell us something about the state of the memory to only tell us what is contained in the cell if the domain of that map is the same as the variable that represents the address of the cell. So in this case, you have a variable L1 that points to this cell, and you have a variable L2 that points, that represents the address of this cell. In this cell, the numeral 1 is stored. So we want a map that when we give it the variable that represents the address of this cell, it returns the number 1. But for any other variable that does not represent the address of this cell, we want it to be undefined.
Yeah, so question mark really means just undefined.
Yeah.
So is L1, I'm not quite sure what a variable is. Is that it's not the same as a memory location, is it?
No.
But then why is L1 and L2 two elements of B? Like is L1 an element of lock? I guess. It is.
Yes.
A lock has 8 elements.
Yeah. But now I'm a little bit confused myself, I think. But is it really important? Like, so in the specification of separation logic, we have variables that represent memory addresses, but we can also skip that. We can also just like look at the addresses directly. So
yeah, like in your earlier slides, you had X and Y, right? Those are like maybe one question is like in some of the earlier slides, you had X and Y that point to the same place.
Yeah.
Is that possible here?
Sure.
So you can have L1 and L2 be the same place?
You can have nicknames.
Is that
let me see.
Those are like A, B, C, D, right?
Oh, no, L1 and L2 are specific values, right?
but
So we
are
can-
L so question is my question is L1 and L2 like the X and Y from the earlier slide?
No, it's not. It's not.
Oh.
So that's like, I'm sorry for the confusion. So in the earlier case you have seen, you have like variables that represent memory addresses. And in that case, we can have two variables that evaluate to the same memory address.
Right, like
they can point to
Those
each
are
other.
constants. L1 and L2 are basically constants.
Yeah, yeah. But in this case, we don't look at variables, but we look at memory addresses directly. So
Yeah.
L1 is a distinct memory address than L2.
Okay, I don't know if you can manage to not. I mean, it sounds like L1 is not what I call a variable.
I'm sorry?
No.
I wouldn't call L1 a variable.
No.
If I make sense, I understand that. Okay.
Aren't these different MIs sort of redundant? If the L's contain the information that you need to access, like why have different MIs for each index?
I'm sorry?
The lowercase MIs, the mappings,
Yeah.
why have a different one for each index? Why not just have text the L?
I think that's just an artifact that we only have one set of integers to some sort of
Yeah.
So when you write M1, little lowercase M1, right? You take lowercase m1 as a partial map from B to integers.
Yeah.
But it only it's only defined on L1.
Yeah, exactly. Yeah.
But you're going to, it sounds like is there some reason you're not taking M1 to just be a total map from A to integers? Like, I think M1, your picture for M1 is just a very leftmost bit of that picture.
Is it okay if I use the board a little bit?
Yeah.
So,
I think it would be better if you picked arbitrary numbers, so those like M17 and M23, and then it wouldn't have this.
There is something wrong in this notation.
No, it's just confusing for us if
Yeah.
we
But look, so we have,
just use arbitrary indexes that are different for 1 and 2 for M.
well,
Because we're making this false assertion that M1 has something to do with L1, and it only incidentally has that assertion, not fundamentally.
there are like different ways that you can define M, and they will all kind of come like have the same semantical meaning. But the reason why I have different maps.
Or call them little m alpha, little m beta, or pick your alphabet.
So MB assigns to B a set of all maps that have as domain the memory regions contained in B to the integers. And what is wrong here is that in that example there,
Here, that's illegible. Here's a better pen coming to you.
But square brackets is like a notation for partial maps or something?
no, like this, it's, do you have like background in category theory a little bit?
Yeah, he does.
It's like,
I don't.
Yes.
Square brackets mean lists.
yeah, it's, you see,
Hom set, right?
yeah.
It's either the functions or the finite.
I'm sorry, square brackets are taken. Y'all come up with your own brackets.
This goes back decades.
Okay, so then let's,
So do square brackets.
Yeah, different groups of people.
so
It's
then
not enough
we will
symbols.
do it like this.
There.
So M assigns to the memory region B a set of all maps from B to the integers. And what goes wrong in my slides here is that there is some M1 that has as domain L1 integers, but L1 is not equal to B. So this is not possible in the way I define the maps. It should be that this map M1 takes the entire subset of memory. And then it makes sense that we have two maps in there. One map that evaluates to 1, that's kind of like, that map lets us access the contents of the cell 1, and another map, M2, that lets us access the memory contained in the cell 2. And the reason for this is because you have a pre-sheaf here, and you want to restrict these maps to smaller subsets of memories. So what you then can do is that we can restrict this map so that we have as domain only the region L1, and then we have some M prime 1 in ML1. So this is just like a map directly with domain L1, and then we can see how they are defined when we restrict maps. And that basically alludes to the fact that the functor M is a sheaf. So if you look at then you can restrict them to their overlap. Because well, both maps evaluated 2, and if you restrict them to a smaller subset, it doesn't change anything to the fact that it points to the cell containing memory region 2. And the Sheaves note says that there should exist a bigger that's defined on this domain, such that
So maybe this is not important, but I don't yet see the need for the question marks, the undefined, because if I don't want to be defined so far, I could just only have a function that, like little m1 could just be the only mapping from L1 to integers, right? And like L2 doesn't even have to be the domain of m1.
yeah.
But maybe, okay, we'll see. I mean, I'll see if that ever matters.
Well, but what if you, for instance, like you don't do anything with computational effects yet, but what if you have some computational effect that allocates the content stored in the memory that are accessed by a map in that thing there. So after the deallocation, then we still have that map, but it doesn't point to anything anymore. So then it's just kind of, you still have a reference of that map, but it's undefined then because we deallocate the contents of the memory region.
So can I just treat question mark as an integer, like as a deallocated integer? Like it sounds like, for example, M1 and M2 cannot be glued together, right? Because they're not consistent on either of these two locations, right? Question mark is just like an integer that's not equal to 1 and not equal to 2. Right? I'm just going to treat that question mark as a special integer now.
But why not bottom? Like,
Sure. Yeah, I don't know.
what if you want to store like a special integer to a cell?
Maybe I can, right?
Yeah.
Like so far, I haven't been told what's so special about this question mark integer. It's just another integer. Sure, I don't know.
But I think it's up to the interpretation of the programming language of separation logic.
Yeah, like these integers don't make. I mean, I don't even know that I can add them.
So if you want to look up something in a deallocated cell, then you can either return that special integer, or it should maybe be something that is undefined behavior, I guess.
Yeah, okay, I don't know.
But I don't think that's...
I think we know what you mean now,
Yeah,
though, so
yeah.
that's good.
I think I've covered this a bit.
It's actually.
I don't think the lighting needs to change.
Larry knows the trick.
I think this is it.
Okay. How's that?
Yeah.
Is that better? That's good. I think there have been some questions on this. If you there's a bunch of questions in this chat. I don't know, like a lot of people are asking, probably wanting to talk here. I don't know.
Yeah. So for the ones who are joining on Zoom, there were some questions in the talk here for people who are present here about the definitions of the smaller maps contained in MB. And I explained that by showing some things on the whiteboard, but I don't think that those that whiteboard is visible for the people on Zoom.
I think we'll pass, I think Tianyu is
Yeah,
filming.
right,
the whole-
yeah. By recording, we'll contain like the
Can I
whiteboard stuff.
access the questions that are asked on Zoom?
I think if you stop that sharing.
Do you have to tell it to sharing? That's too bad.
Yeah. Click on that box.
I think if you just click on the green.
Oh, yeah, sorry. Yeah, sorry. Click on the green.
And then,
No.
The green part,
Yeah, there.
chat 10.
10. Okay, yeah.
oh yeah. So the questions were indeed
People are-
about the. Can I like point this laptop to the whiteboards?
You could point the camera, you could point the top to the whiteboard, yeah.
I don't know if it's
It's
necessary.
not going to be very uniform.
Yeah.
In fact, I don't think the camera will project very nicely with that.
Yeah.
I think it's a bit difficult to answer these questions.
Yeah,
And
we could come back.
yeah. Do I continue now?
Okay, so you need to go, click on your slides, or make it full screen. So, maybe I'll do this for you. Full screen.
So just to recap, we have like memory defines its topology, and we have a way of seeing what kind of contents is stored in the memory, and we also have a way of like a local specification of the memory by restricting the maps that are defined on some larger memory to see how they are defined also smaller memory. So I added some things here that specify a little bit more about why the choice of topology is important, but I think that is a little bit too out of scope for this talk. The thing is that we don't like describe the set of memory locations as a discrete set and or it's infinite, then it might be the case that an open set or open subset of the memory can only be covered by an infinite amount of subcovers. That shouldn't be a problem, but there are two interpretations of separation logic. One that allows for infinite memory arithmetic, and one that does not allow for infinite memory arithmetic. So the way to remedy that, or like to make a design choice about that, is to pose some restrictions on the topological space. And we can, for instance, say that each open set needs to have at least, or needs to be able to be covered in a finite way. And then we also have a possibility of only allowing for finite address arithmetic. So now we have a way to access the memory, but we don't have a way to change the memory yet. How do we do this? Well, if you think about it, when we modify memory, we go from one memory state to another. So let's at least start with a map from some memory configuration associated with ML to another memory configuration associated with ML. That's all good and well, but we should also keep some kind of chronological order of these maps. So let's say that the memory is allocated in a certain way. We change it, and we change it again. How do we do that? How do we keep track of the state of the memory? Well, we combine it with some sets And that set can be anything, but it's just allows us to keep track of the states. I will give an example later on how that will be done. And how do we now transition between states? Well, we start from the current state that is represented by the set x. Then we move from x to a map from the current memory configuration ML to a new memory configuration after we have mutated the memory in a certain way. But after this mutation, we also land in a different state, so we combine that new memory state, new memory representation with a new state y. And we can also chain these state transitions in a certain way. So let's say that we have, apart from the map F, also a map G that goes from the memory state Y to a new memory state Z. Then we can compose the two together to go directly from the memory state X to the new memory state Z. And it also takes account into what the change steps in the memory here. For those with some background in category theory, how do we do this? Well, let me see. Sorry for it. I think a slide has been deleted somewhere, but the way we do it is using monads and Klasky categories, but yeah, just something interesting.
This x is different than this x, right? I mean, that x that you have there is not a variable. Actually, it's not even a set of states. It's a particular state.
The arrow here is not the same as the arrow, I guess.
Yeah, I think what you do, one of those pens is gone. It looks like what you really want is that this T, in fact, we write it as ML goes to, like this thing goes to some other location times x, where this is a particular state. So it's not a function. So this x is not the set of states. Because you wouldn't write it with y as a different letter. You'd have to use the same letter. It's actually a particular state, so it's more like this kind of.
And you're like sticking states isn't straight. I mean, on your next slide, you've got like sets of, you've got like a finite state automata or something. You've got your states labeled.
The states are 1, 2, and 3 there.
Yeah.
Right.
Maybe it will become clear if I have this example a bit more.
Yeah.
I will illustrate how computational effects were being modeled, showcasing what happens in this transition system. So in this transition system, we have 3 total states and 2 commands that do something to the memory. We model state transitions, or like the computational effects, then that's form. That takes any one of those 3 states, and it combines that state with the memory location or the memory specification that is associated with that state. So we have 3 variables in this example, x, y, and z, and we say that the initial state of the system is that x is a variable that points to a cell that contains the numeral 1, y is a variable that represents an address of a cell that contains 2, and z is a variable that represents an address that contains the numeral 3. If we want to model the first computational effect, so we assign the numeral x, the numeral 3 to the variable x. The way we do this is we take the map C, we start at state 1, we give it the current memory configuration, and we say now that the map that used to point to 1 now points to 3, and we get back a state 2. Now we can, now we are at state 2. So we will look at what happens there. We can, as the map you see, we give it the current state 2, and also the updated memory M, so in which X now points to 3. And that gives us a new memory new memory configuration where Z now points to 1, and it gives us back to state 3. And finally, we arrive at state 3. But that is the end of the transition system. So when we see what happens at state 3, we just get back the same memory configuration. So no programmatic effects to self-contained memory.
So it sounds like you're using those states to represent sort of like points in a program or a control, sort of the control flow
Yeah.
of a program.
Does this all?
I mean, this is clear.
Yeah. Now, in this example here, we only have a way to model programmatic effects that modify the whole memory. But we want, the whole goal is to see what programmatic effects do to like a smaller memory. So we, instead of like in the earlier T here, this represents a programmatic effect defined on the whole memory region L. Now we will look at families of programmatic effects, and we index them by the small L here. It is some open subset of the memory. And in order to restrict it, it can take an inclusion morphism from the smaller memory L1, and then maps it to a mapping from the global memory to a new memory configuration that's only defined on a smaller memory. And if you can look at this map, we can then restrict it, give only smaller, well, this is a bit confusing, this notation here. So we have two subsets of memories, L1 and L2. L2 is the bigger subset, L1 is a smaller subset. We have a programmatic effect that goes from NL to ML2, and we can restrict it, given the inclusion of L1 and L2, to a programmatic effect from ML to ML1, the smaller memory. The thing is, the modification of the memory happens from here to here. And as you can see here, the ML here still remains the global memory. So we also need a way to look at the programmatic effect here from a smaller memory. And we do that by taking a complex limit, that is the end, that looks at the programmatic effects from the smaller memory region, ML prime, and it is restricted from the larger memory, ML. I think it's better showcased in here. So we have some inclusion morphism I, Oh no, never mind. So we have now like a way to access all those families of programmatic effects for all open subsets in L. So for all L prime in L, we have a T L prime. And restriction of those families of functions just works the same as linear. So if we have some inclusion morphism I, L1 is included in L2, then we can restrict S of L1 to S of L2. So now we have a way of restricting the memory at the input of the map, and a way of restricting the memory at the output of the map. And why do we want to do this? Well, we now have two ways of restricting memory. One way, if you restrict the first index, then we also restrict the programmatic effect. Now the programmatic effect only operates on a smaller part of the memory if you restrict it. But and the second way, the programmatic effect still operates on the entirety of the memory, but we can only look at a local region of the memory to see what has happened in the programmatic effect. I think I will keep it a little bit shorter. I will now show the main result of all this. So we have two different processes operating on different memory regions, the process P1 and the process P2. And we now want to see if the logic of Sheaves allows them to combine them into a process that is defined on the overlap of the memory L1 and L2. So we want like this showcases how we can compose the processes P1 and P2.
So when you say compose, do you mean sequentially, like
Yeah.
P1 happens first and then P2 happens?
Yeah.
Okay. And so agreeing on the overlap, does that mean something like the final result of P1 has a part of that memory agree with the initial memory of P2?
Yeah.
Okay.
That is what happens. So, like, you can just normally compose them because the domain of the S doesn't really match up. The first process has L1 as its domain, and the second, well, not really as its domain, but like the first process is only defined on the memory region L1. The second process is only defined on the memory region L2. But in order to see if you can compose them, we want to specify the two processes on the overlap.
So when you say defined on, like I'm sorry, I didn't get the S from the previous slide, but P1 reads from L1 and writes to it, and P2 reads from L2 and writes to L2, right? Is that what defined on means?
Ooh.
Sorry.
Yeah. So in any case, like SL1 always reads from the L1, but because of this limit here, like this end here, it writes to L1, but also all subsets included in L1. Like it has it has some kind of compatible way of combining those programmatic effects. So,
but it never writes beyond L1, for sure.
I'm sorry?
But for sure, it never writes beyond L1.
No,
right?
exactly. No, it never does write beyond it.
Okay.
And then the same for L2. It reads from L2 always, just L2. Well, it writes through L2, but also all subsets included in L2. And if you now recall the axiom of a sheaf, so P1 and P2 are sections of classical morphisms, so they're like sections of programmatic effects. If we look at what happens on the memory only on the overlap, and the overlap agrees, then there should exist some computational effect defined on the two memory regions combined, And from that we can know that P1 and P2 are compatible, and we can compose them on their overlap.
So do you end up with something that uses the intersection of L1 and L2? Like, I'm surprised. I guess it starts with what does it mean to restrict? Like I was expecting composition to be just composing P1 and P2, not a restriction of P1 and a restriction of P2. And I realized that I don't really know what it means to restrict P1, because P1 needs to read from all of L1 potentially, right?
Yeah.
So what does it mean to restrict P1 to L1, intersect L2? Like, I think it makes sense to restrict a memory map, but
Yeah.
here we're not talking about memory maps being restricted, we're talking about processes being restricted, right? So what does it mean to restrict the process?
Well, these processes are still defined by the vector S. So when we restrict the process P1 to the intersects, I will use the board, I'm sorry for the P1, so but I have to use the board again.
I mean, the process might read from L1, right?
You might die out because you don't have enough stuff to.
Just say.
Yeah, so this part is the reading part, right?
Yeah.
Yeah, and I'm worried about what it means to restrict this part when L1 gets smaller, right? Like this, sorry, all I do is I write programs, and if I'm told that I have a program that reads from memory, and now I'm instead told I can only read from part of that memory, like L1 intersect L2,
Yeah.
I'm worried my program might not run anymore because it might need some content of that memory in L1 that's not in L2.
So let's say that we have some variable that's contained in this part.
Yeah.
But not in the overlap.
Right. Right. So I
We
might have a
say-
program that just reads it. Yeah.
Like it is defined as we write a variable, we assign something to x.
Well, what if I'm saying x reaching x plus 1? What if I'm incrementing x?
Yeah.
Right. That will read from x. Right. Yeah.
But if you now look at what happens in the smaller region,
Yeah.
it is undefined. So it doesn't
Oh.
it doesn't really matter anymore because it's undefined. It's not compatible on the overlap as well. Because the output of
What if they both are undefined? Is that a kind of a ring? Like if I restrict P1 and it turns out that
yeah, sure, but then the combined process on the overlap is also undefined. So that's
yeah, but
There's
they will agree, right? In
Yeah.
this kind of
so then you can combine them together, but you
Yeah.
will get an undefined process.
yeah. Why do I want this? Why do I want this kind of composition?
Mm.
Does it help me prove something, core logic?
Yeah, but it's just a very good question to ask. Yeah.
Okay.
I don't even know if I have a satisfying answer to that
Okay.
question.
But it does help me understand what kind of composition I get.
Yeah.
Yeah. Okay.
It'd be a good thing to talk about over dinner too.
I'm sorry?
It'd be a good thing to talk about over dinner too.
Ah.
Yeah. But still, let me see.
I see the recapsulate.
Yeah. Okay, so I think it's just best to keep my talk at this point here. I've taken a lot longer than I've expected.
So he was going to mention that you're also planning to work on the probabilistic case as a probabilistic effect. So when he returns in September, October?
Yeah.
I have.
I think I got stuck a little bit too much on the details in this case. But now we have a way of combining programmatic effects to each other. But that's like, these are programmatic effects because of how the map S is defined. Or like, because S is a local state monad. But if we use a different monad, for instance, a distribution monad, then we could extend this framework to maybe different kinds of separation logic. Maybe a separation logic that deals with probabilistic programming. So that is the key point on where I want to end this. Now we have kind of shown a way to combine programmatic effects into each other, but because we can use maybe different specifications of the maps, we can extend this framework to different types of separation logic as well, which is what's the point behind it. I'm sorry that this talk was a little bit messy maybe, but I appreciate your input like a lot actually, like the questions that you have asked. Maybe see that I have to investigate my examples a little bit more. So thank you for that. Also thank you for attending the talk in such a big number. Are there any questions?
Well, Peter has we should thank you first of all.
Yeah.
Peter raising his hand up.
And also,
Can I
thanks
ask
for
you
your
a-
patience with our.
Yeah, no worries.
Yeah.
Could I see the next slide? Larry, thank you.
We did actually.
We should, yeah, it helped to listen to your answers too. So we should let
Peter has his.
Peter, so, I don't know, how about you, Ken?
Yeah,
Can we hear Peter? Can you talk, Peter?
I think I have to give permission to unmute people, or
No, I think you should, if you right click on that, does it say unmute?
We're,
Peter.
Peter, let's see.
No?
I don't know how Zoom works.
Oh, you don't, okay, that's okay. Around everything you're asking, so I should. What should I?
That question in chat is exactly what you
Well,
asked him.
Hi, Peter.
Is this Peter's question? Yeah,
Oh, we
thanks.
can- we can-
I don't know if you want me to ask this question in chat or unmute. Could you unmute and maybe ask it, Peter?
He's unmuted.
We
Yeah.
can't hear him.
Oh, we don't-
Oh, we don't have
Maybe it's about the, yeah.
Oh, we don't have the speaker.
It's our problem.
That's our, yeah. Okay, so I'll just read it.
Yes.
Sorry, Pete.
I don't know if you want me to ask the question in chat or unmute, but could you say a bit about the application of this formula? Like, what does this allow you to do that you couldn't do with a less abstract formula, just checking programs, if they don't make incompatible assignments? So another question related to this is there have been semantics for there have been semantics for separation logic. So why are you doing the sheet theoretic work? What do you hope that this semantics will do that the previous semantics didn't do?
Yeah. So I try to allude a little bit to the fact that there are different interpretations of separation logic. One that allows for finite address arithmetic, and one that allows for infinite address arithmetic. And the sheaf theoretic model just makes it so that if you choose a different topology, you will get completely different interpretation. It's, I think, allows for flexibility.
So is there a property you can define and represent with the sheaf model that you can't with classical models?
Could you maybe give like an example of such a property?
It would be nice to have memory that's continuous.
Like some shared memory situation. What would, yeah.
Continuous memory.
What does a continuous memory mean, like an analog memory?
Well, like memory, like yeah, like maybe when I heat up my pen,
Yeah.
that's my surface of my pen is memorizing its temperature.
Mhm.
Yeah, I guess you can model it just as well as the discrete case.
So there I had to omit a little bit of this talk, thinking of what I can tell so that it's comprehensible, and also maybe tell us a bit more about why I use the approach of Sheaves. So I think it's natural to investigate the logic of Sheaves in the context of separation logic. Separation logic just facilitates the combining of these local perspectives to like a global specification of a program. And Sheaves, as you've seen, allow for the same possibility. And my hope here is that it can provide some unified framework that kind of uncovers the core of this separated conjunction, of what it is, what the separated conjunction does, that it allows for this pasting, like, or like gluing back these local components. And in this case, I've shown like the example that is related to computational effects. But if this framework can uncover the core of the separated conjunction, then instead of just computational effects, then we can very easily extend it to some other extension of separation logic. So that is the main idea behind this approach. Like, I don't know if the way that semantics have been given before of separation logic, what you would have to do to those frameworks to make them extendable towards, like, to other ideas of separation logic. I think that it's complicated to do that, and I hope to maybe see if it's like more natural to extend my framework to other extensions of separation logic. I hope that answers your question.
I feel like the golden ticket is if you can find some property, formula, constraint, something that you can model in the sheet theoretic framework that you can't model with other semantics. I can't think of one off the top of my
Yeah.
head, but
Yeah.
if you had that, I think that would be a great pitch.
Yeah. Okay, that's, yeah, thank you.
Okay, we should thank Berend for the nice talk, for coming. Everybody, thank you for coming on Zoom too. If anybody has to run off, feel free. Good to see you all. We'll be in touch with you.